Everybody.
There we go.
Yeah, press this. Okay. So good morning, everybody. In this seminar, I will give you an introduction to observational astrophysics, let's say in the field of multi-messenger astronomy. Okay. So I set the seminar for an audience of Master 2 PhD level without a background in astrophysics. So in case you already have a background in astrophysics, maybe you will already know many of the things that I will say. Sorry about that. So can you hear me well? Can you see well my slides? Yes. I go ahead.
Yes, I think audio is good. Slide is good. Let me check, because we had problem during the week that some of the slides appeared fuzzy for some of the participants. Is this okay? Are there any issues today? Seems like it's okay. All right, go ahead, Susana.
Okay. Okay. Let's start this kind of a travel. It's a quest towards the detection of the electromagnetic counterpart of a gravitational wave event. Okay, so we have an alert from LIGO Virgo detectors, and we start our quest to detect the electromagnetic counterpart, to identify it, and to characterize it. So we have these three steps, all of them fundamental. In fact, detection is mandatory, is really the first thing that we need to do. But with the detection, we don't have any astrophysics to be done. It's just the detection of the counterpart, of a transient that can be the counterpart. Then the fundamental step is to identify that it is the right electromagnetic counterpart associated with the gravitational wave event. And from this step on, we can start to do some astrophysics, so it becomes interesting for science. And then the very step to really do science in both astrophysics and physics is the characterization of the electromagnetic counterparts. So this is really our aim, our final goal. But to reach it, we have to go through the other steps. So today I will focus mainly on the detection part and a bit on identification, and really from an observational point of view. You will have next week lectures from Giancarlo Ghirlanda. Then we'll talk much more of the characterization of these electromagnetic counterparts, and also talk about it from a more theoretical point of view and physical point of view. So, okay. So I will only focus on LIGO, Virgo, and Cagra, the future Cagra events, and only on the merger of neutron star binary systems that you will see notice as neutron star or BNS. Okay, I have no time to talk about the far future or about other gravitational wave events like those detected by LISA in the future or so on. So what are the electromagnetic counterparts that I expect from a merger of the binary neutron star system? I have different kinds of counterparts. So one of it is the kilonova. Then I have what is called the relativistic jet that we think associated to what we know being a short gamma ray burst. And then I have another electromagnetic counterpart that is not really the counterpart of the gravitational wave event itself, but is the electromagnetic hosting object of the merger. So that can be a galaxy or a globular cluster. This electromagnetic counterpart, the real electromagnetic counterpart, so the kilonova and the relativistic jet, have also a very important characteristic that they are transient. So I cannot observe them forever. They are bright for a certain period of time and then they disappear. So since they are electromagnetic counterpart, you will see we will use the entire electromagnetic spectrum to try to detect them and to study them. So just a slide to show the way the way astronomers observe the sky at different frequencies. So you have the electromagnetic spectrum from gamma rays to the radio. And you will see that there are some windows that can be observed from the ground, like the optical one and the radio one, and the other that for which we need to go to space because the atmosphere absorbs such frequencies. So we need satellites to observe the sky. So as I said, we will use the entire electromagnetic spectrum because astrophysical objects looks very differently depending on the frequencies at which we observe them, because of course every part of the electromagnetic spectrum is sensitive to different kind of physical processes, and therefore depending on the frequency, I see different things. I can observe different things and different mechanisms, different processes. Here I show an images of a galaxy observed with different instruments. So from X-ray satellite from the space to radio observation. And you see that the galaxy look completely different depending on the frequency at which I observe it. The X-rays are very sensitive to the hot gas. In the optical, you will see also, for example, the absorption from the dust that is present here in this region. In the radio that is sensitive to synchrotron processes, you see the jets. And for example, in a very specific frequency of the radio, you will see the presence of hydrogen. And all together, they will give us the full picture of the galaxy, okay? So if we want to understand an astrophysical object, we really need a multi-wavelength approach. So before going on, I will have to focus a bit on this part of the electromagnetic spectrum, that is the optical window. Because I need to introduce some symbols that you will see in the future of the slides. So in the next slides, so you will, when we observe in the optical, we observe using different filters, okay? So from the ultraviolet to the infrared, near infrared, you will see filters that has this name, UV, VRI, or these names. Those are different filters, okay? It's just because in the next slides, you will see some of these symbols. So you know that they correspond to an optical filter used for the observations. Of course, it's kind of like that. Every filter is on typical frequency or wavelength as you want, and a certain width. You will see here, you see here some of the filter I mentioned before in function of wavelength, okay? So when you see these symbols, you know what I mean. And then before starting to go through this quest, I must say that what I will show is based only on the knowledge we have from models, so a theoretical knowledge, and observation is based mostly on one event, okay? That is, of course, the GW170817 event, for which we have a fantastic campaign that allows to go through all the three processes to detect identification and an excellent characterization as well, okay? So let's start from the kilonova, and let's start just to give you a few information on what...
the filter.
Sorry,
and
sorry, I can hear some voices. Okay, so I will give you some indication on what, really from an observational point of view. So not on the theory that produced the kilonova emission, but from a point of view of an observer, what I expect to see, okay? So the kilonova is produced by the merger ejecta. And from an observer point of view, what I see is a blue component that is emitted towards the pole, let's say, mostly, and is a fast component that is visible. It's called blue component because it's visible in the blue optical filters, okay? Then we have a red component that is lower, rich of neutron, and it's visible in the near infrared filters, okay? So if to observe a kilonova, I will use these optical frequencies, and in particular, I expect a component in the blue that is erased, they say it erases very fast, but decays also sooner, and a red component to be observed in red or near infrared filters, okay? Of course, what I will observe, it depends on the viewing angle that I have, okay? So the viewing angle on the pole, it's what we call on axis, okay? And as soon as we move away from this angle, we increase the observer viewing angle, and we call off axis this, let's say this point of view of the observers, okay? So as you can see immediately, if I am off axis, there is a chance that I will be completely blind to the blue component and will only see the red, and vice versa. On axis, I will be very sensitive to the blue and also to the red, but I will not miss the blue component, okay? So in the next slide, I show you what we saw for the counterparts of GW 170817, so as to give you an idea of the only one well-characterized observed kilonova, okay? So here is the light curve. What is a light curve? So a light curve is the variation of the flux of our astrophysical object with time, okay? So here is a time scale in Julian Dane that is a strange astronomical time scale anyway. And here you see each colors correspond to a filter. And these dots are the observed point, okay? And the lines are the fit of the points, okay? So here you have a unit that is apparent magnitude that if you are not an astronomer, let's say you don't know it. It's a very strange unit, let's say. In astronomy, we have a lot of strange units. So apparent magnitude is a unit that we use to quantify the flux of our object, and is related to the flux towards this formula. So a magnitude at a certain frequencies, an apparent magnitude at a certain frequencies or wavelength is linked like that, let's say to the ratio of the flux at this particular frequencies and the reference flux at that frequencies. So we have also different system of apparent magnitude depending on the reference system that we use, okay? Just to tell you two names, the one that we use are the Vega system and the AB system, just to give you some notes on that. Anyway, it's not, you don't have to care about this system for this talk, but just you have to care that the apparent magnitude is the quantity that we use to talk about the flux of our object. And it has this counterintuitive peculiarity. There's that fainter object have larger value of apparent magnitude, okay? So this is bright, this is faint. And you can see that, our light curve of the kilonova decays with time. I want also to stress another point, is that the flux in astrophysics, the flux of the object is linked to the luminosity, the intrinsic luminosity of the object through the dependence of the distance to the square, okay? So for a distance that is, if an object is at a distance that is 10 times farther, its flux is 100 times fainter, okay? This is different from gravitational waves where you have a linear dependence, okay? So distance is an important quantity for us. Here you can see the blue part of the kilonova, okay? As I say, the blue component that, as you can see, is bright in this blue filter, but decays very quickly. And then you see the red component here that becomes important a later time, that emerges a later time, okay? Thanks to this fantastic set of data, it has been possible to study precisely the ejecta components of the kilonova, the velocity, the ejected mass, and therefore having a lot of information on this neutron star merger system. So then we can also detect the kilonova study the kilonova through spectrum, so through spectra. So here you see the spectrum of the event of 170817, and you can see the evolution of the spectrum in function of time, okay? The spectrum is the flux in function of wavelength. You have it here. And so you can see also from the spectrum, this blue component very present at the beginning, and then the red part becoming more and more bright. And this spectrum was extremely important because it allows us with the light curve to determine the presence of heavy elements produced by the kilonova that in the spectrum are causing these bumps that you see here. Okay, so the famous lanthanides, this is what is thought to cause these bumps in the spectrum, okay? So then we have another, in fact, electromagnetic part that we can detect linked to the kilonova that is due to the shock of the kilonova, of the merger ejecta, with the interstellar medium, okay? So this is what can be called the kilonova afterglow, and is supposed to be detected in the radio, but also probably at other frequencies. I will not talk about it because there are observations now ongoing that could be probed this part. And since we are still not sure what we are seeing, I will not touch about this in this seminar, okay? So that's all for the kilonova, let's say, characteristics. Let's, from the observational point of view, let's go through now the relativistic jet part that we think is related to what is commonly observed as a gamma ray burst. Giancarlo Ghirlanda will talk a lot about gamma ray burst next week, so I will not go in detail about that. But I want to just tell you from an observational point of view what we do expect to observe. So first of all, we expect to observe gamma rays. So gamma rays, that is really this gamma ray burst, this jet that is produced and that will go out from the merging in the pole direction of, from, let's say, if we suppose the equatorial plane here. So we will have some energetic gamma rays, very energetic gamma rays, let's say in the on-axis direction. That is what we really know as the gamma ray burst, and those have energies greater than 10 to the 50 Earth. And then we have also a fainter gamma ray emission that can be seen off axis that can be due or to the lateral structures of the main jet here, or to some interaction with the cocoon that is produced during the jet emission with the surrounding medium. Okay, so this we are not very sure, but anyway, we're supposed to have an energetic gamma rays on axis and a less energetic gamma rays off axis, less and less energetics as we move away from the zero viewing angle. Okay. Then the other component that we expect to observe is the relativistic afterglow, the relativistic jet afterglow. So what is the afterglow? In fact, the afterglow is an emission that is caused to the shock of the jet with the interstellar medium, okay? So surrounding the neutron star system, there is what in astronomy we call interstellar medium, that is formed by gas, dust present in the galaxy, okay? So when the jet shocks again the interstellar medium, it produces this afterglow that is observed at all the frequency, actually, from the X-ray to the radio, okay? Again, also for the relativistic jet part, what we see will depend on our viewing angle, okay? So here is to show you some example related always to GW 1708-17. This is the gamma ray detection that has been performed by the Fermi and integral satellites less than 2 seconds after the gravitational wave event, okay? And this is the relativistic jet afterglow. Is a collection of all the observation corrected by the spectral index, so as to be able to show you them all together here. So you can see a rise, a peak, and a decay. And you can see that this observation has been taken, these observations have been taken at very different frequencies. So you have X-rays. This is Chandra, that is a satellite that observes in X-rays. You have optical points from HST, that is the Hubble Space Telescope, and you have radio points from all these other facilities listed here, okay? this observation has been really fundamental for us that study gamma ray burst, because they allowed us to really study in detail the structure of the jet. Then I end the list of the observational property of the electromagnetic counterparts with the host galaxy. So as I said, we expect that binary neutron star mergers happen or in, let's say, galaxies, standard galaxies, as I show you here an example, or in globular clusters, okay? So globular clusters are not galaxies, are a cluster, very dense, of stars that are gravitationally bounded and that are found in the halo of galaxies, okay? Sorry. So this electromagnetic counterpart is very important. As you will see, it can help to detect the other counterpart. It can help to detect the other counterpart, and is very important because when we determine the redshift of this galaxy, we can use the information to joint with the gravitational wave information to determine the Hubble constant with much less errors. And it is also very important to study the environment of the binary system. And this is important to determine which is the evolutionary channels of the stars that bring two maxi stars to form a binary system of neutron stars, okay? So now that we saw what we do expect observationally from all these counterparts, we can start to see how and if we can detect them, okay? So let's start from an event, an alert that reaches us from the LIGO Virgo and CAGRA collaboration. What do we have as information to start our quest, to try to detect the electromagnetic counterpart? So we have two important information, the sky map and the distance. So you can see here what the information that we have looks like. This is from the GraceDB database. We have a distance with a certain distribution, and we have a sky map localization, and the colors correspond to the probability of the region to have host the event. So the gravitational wave event linked to these distances map has a high probability to be happen here and less here, okay? So I will show you different examples of these sky maps, because they can be very different. Here we have a very, very extremely poor localization, because it's of the order of 10 to the 4 degrees square. So it's almost let's say the entire sky. So we really don't know where this event took place from an observational point of view. From an electromagnetic observational point of view, this is the situation. This is our perception. Then we can have intermediate cases with the localization of the order of 10 to the 3 degrees squares. Is better, is not great, but it's much better than the other case. And then here I'm cheating because this is not a neutron star merger, but fine, it doesn't matter. We can have similar distances and maps also for the gravitational wave from binary neutron star mergers. And here we have a very nice case, let's say a pretty nice case with the localization that is very good from the point of view of LIGO Virgo CAGRA. From the electromagnetic observational point of view, is still not very good, but since we can be in the other much worse case, we are very happy when we have localization like that, okay? So the order of 10 degrees square. So then there are other two factors that you have to take into account when, for our quest towards the detection of the electromagnetic counterpart. And in particular, I start talking here of kilonova, about kilonova. So the flux, or the magnitude as you want, are not so bright. They decay with time, as we saw, and they become fainter with distance, okay? So in this plot, you see the fluxes, so the observed magnitudes in function of times. in two different filters, the R band here, the H band here. So here in the visible is in the near infrared. And you see the expected kilonovae light curves, okay? At different distances. Here the distances are indicated with the redshift. I put you here in case you are not common with redshift, the more or less the corresponding distance is in megaparsecs, okay? So the blue and the red curves can be very typical of the next O4 and O5 runs, okay? So as you can see, the flux is really decreasing with the distances, okay, and in time. And the predictions depends on the presence or not of the blue component, okay? So here you have a blue component, here you have not, okay?
Susana?
Yes?
Can I interrupt just a second? Maybe it's worth posing because I see there are a couple of questions there in the chat that
okay.
we'll be asking. Maybe it's a good time for posing and get questions from the audience.
Yes.
The first question is from Chiara. I read it unless Chiara wants to ask straight.
No, go ahead.
Okay. Can one determine the redshift with the previously described emission or only with the host galaxy / globular cluster?
Okay, to the precision that we need for H0, we need the galaxy because in the kilonova spectrum, you will have a velocity in the lines of the spectrum that I would use to determine the redshift. That depends on the kilonova velocity. So they will not be precise enough they will not give us an indication of the redshift of the event precise enough to be used, for example, to determine the Hubble constant with the gravitational wave information. But we can also determine redshift from them, in principle, simply not so useful, let's say.
Right. The other question, oops, there's another question from Vergani. I read it as well, okay? Can you explain what is the reason behind the early blue emission?
I can, but Giancarlo will do it next week. So in very detail. So I will not use time here, but it's due to the wind around the merging systems. Okay, this is what I can tell you. Okay, it's what we call the wind component, but you will have more information next week. I still have many things to say in this talk. Sorry.
No problem. Okay, are there any other questions for Susana since we took some time to break? No, it doesn't seem so. So let's go ahead. You can resume your talk.
Okay, so here is another example of the kilonova behavior. Don't look at these horizontal lines. We will talk about that later, but just on the points here. So you have the expected light curve in different filters here for a certain velocity ejecta of the material and for different ejected masses, okay? But again here, what I want you to see is that the flux decreased pretty rapidly in function of time. This is the time in days. And also that as I go farther in distance, the fainter become the flux, dramatically fainter for some cases, okay? So what do I need to detect the kilonova? I need observation that cover the sky map and that reach the expected magnitude. And I need to perform such observation in a quite small amount of time, okay? Because then the flux becomes fainter and fainter and disappears, okay? And in all that, you have to take into account that our telescope time is limited. So we cannot, we don't have hours and hours, hundreds of hours of time to use for this research in general. There are some telescopes that are dedicated to that, but most of them are not. So we have to fight to have time to perform our observations, okay? So do we have such facilities that allow us to cover the sky map and reach the magnitude in a small amount of time? So if I take here the sky projection, I will show you the field of view of different telescopes. So the field of view is the part of the sky that is visible, observable, with one exposure of from a telescope. So the larger telescope, that means that the telescope that have a larger mirror, that means that are the more sensitive, have a really a very, very extremely small field of view, a dot, as you can see here. Then we have a very small telescope that, on the other hand, can have very large field of view. Very large for us, of course, is nothing compared to the big sky map that we may receive, but it's very large. And then we have what we call survey telescopes, that are telescopes that survey the sky continuously or part of the sky for different reasons, but also for look for transients, that have kind of intermediate field of view or the order of some degree squares, okay? So here I show you the example that I showed you before with this localization that is more or less of the size of these survey telescopes field of view, okay? This is an example of telescope, the Vera Rubin telescope. I will talk more about that later, but we have a problem. So we have a problem that, okay, you may say, oh, I take a small telescope, I survey all the sky and I will find something. I survey all the sky map and I will find something. The problem is that usually the larger is the field of view of a telescope, the less sensitive the telescope is. So if we suppose these lines drawing from a brighter to fainter object, okay, for telescope with a large field of view, I have sensitivity only to the brightest objects. And I will miss the objects that are or intrinsically fainter or simply more distant, okay? And the opposite is for the larger mirror telescope that have a very small field of view, but are able to detect the faintest objects, okay? So this is for a given same amount of observing times, and then we see times matter for these transient searches, okay? So if we want to cover a large part of the sky, we try to use smaller telescope with large field of view. But if we want to recover faint objects, we need a larger telescope, and we need to do it fast. Do we have such instruments? So fast, yes, because nowadays most of the telescopes can react very rapidly to alerts. So they can be on sky very soon, very rapidly. The other two, a compromise with these two is more difficult to have. To have a telescope with a large field of view, but also capable to detect faint objects is really tricky. But we are improving towards this direction, and we will have very soon a very good telescope for that. So if you take this plot where you have the field of view in function of the collecting area, that is the sensitivity of a telescope, you will see that this Vera Rubin telescope, in particular a survey that is called the LSST survey with this telescope, has very kind of good characteristics that can be used for the follow-up of gravitational wave events, because it's very sensitive and also capable to cover some tens of square degrees. And furthermore, it's very rapid. If we scan the sky every such, let's say 2-3 nights, depend on the cadence that we use for the survey. So we are improving. Here is, we come back to the slides, to the previous slides, and now you can look at the horizontal lines that are the flux limit that are reached by different surveys with different amount of time. And this is the LSST, this one, the purple one. And as you can see, it is really a game changer, okay? The situation nowadays is more represented by the ZTF points, that are these ones. Okay, a bit more decam, okay, but LSST will really change our capability to detect such transients. So as we said, what we see depends on our viewing angle, and the simulation that I showed you before are for blue component from kilonova with the blue component, for which we are sensitive to the blue component. But if we take away this blue component, that's supposed to be really off axis with the large viewing angles, the situation becomes more difficult, because in some cases, even with the LSST, we will not be able to detect these kilonovae. And this is due to the fact that we lack sensitive transient survey telescope in the near infrared, okay? That would be needed to detect the kilonova, the red component of the kilonova. So here is also another example of the fact that some prediction in the future, some simulation that show you that we expect to detect mainly the number of detection in function of the viewing angle versus the viewing angle. So we expect to detect mainly kilonovae from events that have a small viewing angle, okay? So for the one, a large viewing angle, the quest will be much more difficult. So to conclude about the possibility to detect kilonova, this is more or less the situation. Do we have instruments that are able to detect this kilonova? It depends on the distance, and it depends on the sky map. I have different cases depending on the distance and the sky map. But LSST will really be a game changer, and we hope really that it will detect many of these transients, except maybe the very far ones or the very red ones. So this is just a plot to recap how goes the probability of success in function of different parameters. So the distance mainly, the sky map extent, and the viewing angle. So when these parameters increase, our probability of success decrease, okay? And of course, sometimes we can have both of them together, a combination of the two or the three of them, and of course the situation is worse and worse, okay? Here on the viewing angle, I say that if the viewing angle improves, the probability of success decreases, except maybe for the on-axis event, and then we'll talk about that in a few minutes. So let's now talk about the relativistic jet afterglow. As we said, it can be detected at different frequencies. So let's start from the optical ones. So here I have a simulation of the optical light curve of the relativistic jet afterglow that has been done by a colleague of mine, Sharm Salafia, that I thanks a lot. So you have the fluxes in function of days, of the time. So for different viewing angle, from off axis to very from on axis to very off axis, and from different redshifts. Okay. So here you can see that, of course, when we are on axis, the object is bright, so it's very good for us, but it decreases pretty rapidly. After 1 day, it becomes already below the magnitude limits of LSST that I showed you before, okay? So we have to react really fast. And also another thing that I want to stress is that this is a simulation following the parameter of the event connected with the JW170817, but the light curves can be different depending on the viewing angle of the jet structures, on the burst energetic, because for brighter bursts we will have brighter afterglows, and from the density of the interstellar medium. If the interstellar medium of the 2017 event was particularly faint, 10 to the -3 or less electrons per centimeter square. If we have a bit more dense event, we will have brighter light curves, okay? Except for very dense events for which we will not have brighter light curves because the flux will be absorbed by the ISM, okay? So here the situation, as we said, on axis is good, off axis or high redshift become faint, as here, or extremely faint, because in fact such magnitudes can be reached only with the best instruments we have. So those with a very small field of view or the Hubble Space Telescope, for which is very rare to have time and to react rapidly. So, but we have also other frequencies, other windows at which we can observe the electromagnetic counterparts, the afterglow of the relativistic jet. So the X-rays in particular and the radio. I show you here the X-rays. You have more or less the same situation of before, okay? And if the localization is not precise, as for the optical case, we need satellites that are capable to rapidly scan in the sky in order to cover the sky map, okay? And they have to be rapid because the flux decreases pretty rapidly again. Here I put the limit, the observational limit of the best satellite we have at the moment, that is the Swift satellite. So as you can see, for the faint, for the off-axis event, we are at the limit of the sensitivity, okay? Or we can be even beyond. So apart from Swift, what do we have? So are we able with this, with the X-ray satellites to really scan the sky quick enough? So Swift is very rapid, but it has a pretty small field of view. And I put you here a comparison with the future satellite that is a French collaboration between China and France. So it's called SVOM, that will be launched by the end of 2022. That is for which the X-ray telescope has a bit larger field of view. So this is a comparison of the coverage of a region of about 2 degrees squared by 2 degrees squares using Swift or using SVOM, okay? So as you can see with SVOM, just 4 points are enough to cover the region. Swift needs many more points, but as in the optical, we have the same problem that a large field of view corresponds usually to less sensitivity. So if we want to cover the same region and reaching the same limiting fluxes, let's say, at the end, we will need the same amount of time from both telescopes. On the other end, we can also choose not to go fainter, but to cover quickly all the sky map. And in this case, VOM will do a very good job. So if we now look at the radio light curves, again, I have the simulation by Ohm, and the simulation I have is at 1.4 gigahertz. You can have many different radio frequencies, okay? I chose this one because the surveys, the White Sky surveys at the moment, the most sensitive outperform at such frequencies, okay? So here again, please take into account that these curves can vary a lot depending, sorry, there is, okay, here there is, depending on the burst property, the gamma ray burst properties, but also that varies depending on the frequencies, okay? So weak burst will peak earlier. At lower frequencies, you will have lower peak flux. So if I observe this, if I do the simulation at 8 gigahertz, I will have something here brighter, and that peak at earlier times, okay? So as you go at lower frequencies, you will have lower peak flux and later times of these peaks, okay? So, but anyway, this is just an example, but please consider that it's just a simulation with some particular parameters. So you can expect much higher or much fainter values, okay? So in the radio, we have a bit more time because the peak is later on, also on axis, also for those axis cases. So is after 1 day, 10 days, or even more. And is also, let's say, quite bright in the sense that current facilities can be able to detect this off-axis emission. But again, if the sky region is large, I need the sky scans. And this is the limit of the surveys, the radio surveys of nowadays. So they can scan in 1 hour, 10 square degrees with such limiting fluxes, okay? So it's doable, the detection is doable at small and intermediate off-axis angles. And if not, it becomes more and more difficult. Then there is the gamma ray emission that is also related to the relativistic jet. So can I observe it? To observe it, I need to go to satellites, okay, to use satellites. And I have 2 satellites mainly that can do the job. The Fermi satellite that can observe all the sky, always, so almost all the sky, so a very large field of view, and as a localization that can be pretty good, okay? then we have the SWIFT satellite. So the field of view is a bit smaller, but still pretty large, okay? And it can give us a detection with the SWIFT satellites can give us a very nice localization, let's say, at least for our electromagnetic point of view. So in case there is a gamma ray emission from the electromagnetic counterpart, and in this case it is bright enough so that one of the two satellites can detect it, the gamma ray emission really helps, because in case of large sky map regions, it really helps in having a better localization of the event. There is also a kind of the perfect case, let's say, for detection. That is, if I have an event that is seen on axis and it is detected by SWIFT, because SWIFT can immediately observe the event also at a lower frequency, so in X-rays, for example, and it can give us the most precise localization, so arc seconds. That means that the best telescope in the world can go and point in that direction, because we know exactly when the event is. So this is the best case for the relativistic jet and for the host galaxy also detection, but it has some issues in the sense that since I am on axis, I will lose many aspects of the jet physics. In fact, the event of 2017 allow us to study the jet physics in extreme detail. We couldn't do it before with an axis gamma ray burst. And the other issue is that we can miss the kilonova, because if you are on axis, the afterglow is bright and can be bright enough to obscure actually the kilonova. So I will have not access to the information that are related to the kilonova, and this is a bit of a pity. Okay, no, this I don't. So to recap for the relativistic jet situation for detection, here again, the probability of success, the changes in the probability of success depending on different parameters. The viewing angles here counts really a lot. And there are also other parameters that count a lot, that are the burst energetic and the interstellar medium density, okay? So to conclude about detection, I will run quickly in the host galaxy, because the host galaxy can really help also in detecting the transients. So I will be brief because my time is almost over. Even if we started a bit later, so I don't know if you can take this into account. Eric, you tell me. Can I use other 5-10 minutes or not?
Yeah, sure, no problem. Okay,
so the host galaxy, to detect these galaxies, okay, galaxies are many in the universe, okay? There are really many galaxies. How can I choose which one is which galaxy to observe to find this the host galaxy of the event? I have to select galaxies that have the highest chance to be the host of the binary neutron star mergers. So how can I recognize them? In fact, there are different evolutionary channels models that, starting from two massive stars, arrives to the two neutron star binary systems, and that merges at the end, and it takes a certain time, few giga-year, let's say. So I can put these evolutionary channel models in galaxy simulation and find out what are the properties of the galaxies that have the highest chance to host a binary neutron star merger. So it turns out that they should be massive. That from an observational point of view means bright in the near infrared. And they should have some star formation rate that from an observational point of view brings that are bright in the UV visible, okay? So my opinion is really to go for massive and then put some weight on the star formation rate. Why? Because if from the experience of gamma ray burst, the host galaxies of short gamma ray burst, for sure they are all massive. And some of them has some star formation rate, but others have very poor star formation rate. So please focus on massive for sure. To do the galaxy host, we have also another kind of data that we can use and that we didn't use so much by now. That is, I mean, for the other electromagnetic counterpart, that is the distance, okay? So the gravitational wave alerts give us also the distant information. This is very important. So to go and detect the host galaxy, I will use galaxy surveys. So galaxy surveys are, let's say, surveys that have been performed in the past and that collect, observe, or the galaxy in the sky or in a fraction of area of the sky. And I will select galaxy surveys with information on the distance of the galaxies and on their magnitudes, okay? So I will use this as the catalogs of these galaxy surveys as basis, and I will observe galaxy in the sky map that I have from LIGO Virgo alert by prioritizing the high improbability sky map regions and the galaxies that have the expected distance and properties following the models and the distance information, okay? This is exactly what has been done for GW 170817. I show you here the sky map, okay? And in the dots here are the galaxies that had the right distance, okay? And their size is proportional to the most probable properties corresponding to the possible host galaxy, okay? So we observed different, all of them with the sequence depending on the probability following the properties of the host galaxies, and we detected the host galaxies of the event. And it's thanks to this search that we could detect the kilonova. So to detect the kilonova, in this case, we used a galaxy targeted observations, okay? So to do that, it helps the fact that luminous near-infrared galaxies are not so numerous for a given sky region. So the galaxy density at high luminosity is poor compared to fainter galaxies, okay? But again, we have the problem of sky coverage in the sense that galaxy surveys that cover the large part of the sky are not sensitive to faint objects, okay? So if I put here, if you see this plot, it means that for down to a certain apparent magnitude, so down to a certain flux limit, my survey detects all the galaxies. So all the galaxies that are brighter than a certain magnitude have the distant information, the magnitude information, and so on. And then as I go to fainter magnitudes, I start to be less and less complete. So there will be some galaxies that will not be present in my survey, for which I will not have information. So in my quest to detect the host galaxies, I have two issues. One is the catalog incompleteness, and then I have also another big problem. So that is the observation incompleteness. Why? Because if the sky map is large, or if the event is distant, I have a larger and larger number of galaxies to observe, okay? So, and my telescope time is limited, and furthermore, I need to do this observation pretty quickly, because at a certain time, after some days, the kilonova become too faint, okay? So I have these two issues. I will not go into the detail, but this is the situation we had in O3, for example, for the neutron star black hole event, and we published it as engraved collaboration. So I will not have time to describe it, but even with an event with such good localization, okay, we weren't able to cover all the probability space to have an event, to have a counterpart, a kilonova counterpart as faint as the one linked with the 2017 event, okay? Even using the best facility in the world, the best survey in the world, and the best facility in the world. So this is really a problem. I will conclude briefly on identification. So let's suppose that we were able to scan the sky map, and we're able to do it with enough sensitivity, so to be able to recover, in principle, the electromagnetic counterpart, okay? So we will have different transients detected in our observation. How we can identify which is the right one? okay? So to identify that the transit that I detected is the electromagnetic counterpart, for example, the kilonova, I need information on the light curve and or on the spectrum, okay? So here I have some problem because if the object, the transits that I detected are faint, or if there are many candidates, okay, many transits detected, it's very difficult to identify which is the counterpart for many reasons. So if I have large localization, even if the LSST will scan all the sky region, LSST will find millions of transients. Even if when polishes some of them, I will be left with hundreds of transients. So how can I identify which is my counterpart? Okay, I show you here. And okay, sorry, I missed the point here. Sorry, it went. Okay. I don't know what's happening. Okay. So how can I decide which is my counterpart? Okay. So, and if it is faint, again, I have a problem because I can, let's focus here, for example, on the yellow or green light curve. LSST will detect my counterpart, but it will detect with a point, 1 point. So I will have many transits detected with the 1 point, 2 points. How can I recognize that his 1 point counterpart is my electromagnetic counterpart? So the identification is really a problem. Many times you see papers that deals about detection, but detection is just the beginning of the story, okay? Especially for faint targets or very large field of view. In the radio is the same, okay? The radio will be able, for example, to detect something. Let's suppose here I will have some points with errors. Already there will be like tens of days after the event. How can I associate that something 10 or 20 days after is linked to my event or is not linked to another transient that is at an origin at that time, at that epoch, okay? Furthermore, it is a late time. So at the other frequencies, the light curve are really, this is the case of the afterglow, are really already very faint. And so how can I characterize it to know that is really my transient? In this case, I would need to observe the relativistic afterglow, for example, in the optical and in X-rays, so as to be able to say, yes, is this one, this is my electromagnetic counterpart. I need really the best telescopes, the ones that are really, really sensitive. So the time of this telescope is really rare to obtain. And so it can be done for few objects, but not if I have many transients like that to be observed in order to identify which is my electromagnetic counterpart, okay? So spectroscopy also is very difficult. I run my time, so I have no more time, so I will not deal with spectroscopy, but it's the same. I will need really the best telescope to do spectroscopy. So again, I can do it for some objects, but not for all of them. So to conclude, we started from detection, and we see that it is tricky, but we can detect our electromagnetic counterpart. Unfortunately, detection doesn't bring any astrophysical knowledge if I don't identify that those are my electromagnetic counterpart. So, and if I don't characterize them. So already with the identification, I can do something, because if I identify those galaxies, I can use the information to determine the Hubble constant. I can use some spectral features to infer which element can be present in the ejecta or produced in the ejecta. I can determine some properties of the kilonova ejecta, even with 2-3 points of the light curve, because I can see if I have a blue component or not, try to determine a velocity. But okay, these are just some very basic and rough information. To do the real physics and astrophysics, I need a characterization. That means I need really to follow them up for a long time, to follow their light curve, and to have very good spectroscopy, okay? So as I said, you will listen more about that next week. So last slide. This quest for the electromagnetic counterpart is challenging, but it's not impossible. And potentially it has extremely high scientific return, as the one that we had for the event of 2017. So even if it's very difficult, it's a very difficult quest, especially to go through all the 3 steps. We will keep trying, and we hope to have many more detection as the one we have 3 years ago, almost 3.5 years ago. Thank you very much.
Thank you very much, Susana, for this very interesting overview. I have a general comment before we move to questions, and there are a few of them in the chat already. Please, I mean, if there are other questions, please feel free to put them in the chat as well. I'm struck actually that in a sense, it seems that already we are limited by electromagnetic electromagnetic limitation, right? Observational limitation with respect to gravitational wave observation. Although, you know, we have a much longer story of observing the sky in electromagnetic waves. It's striking that it happens so fast, right? That we basically are able to pinpoint source in gravitational wave that will take some time to get in the electromagnetic wave. It's probably a sign of how much energy is actually emitted in gravitational wave with respect to electromagnetic wave from those compact sources. You know, I think it's an interesting historical point. I'm not sure whether you want to elaborate on this.
Yeah. So it's true. Partly, I would say that for us, the limitation of gravitational wave detectors, let's say, is this localization. Okay, so I think that this is really what we would like you to have to improve, you in the sense gravitational wave people, because it's rare to have a very well localized event. From the problem from the electromagnetic point of view, to me, is the distance, in the sense that, as I show, even if you have a pretty well localized event, but is quite distant, so that was a 250 megaparsec, the one that I show, okay? So quite distance is nearby, but okay, it's more distant than the GW17 or A17. As we deal with electromagnetic wavelength, this becomes soon a problem. To go faint enough, rapidly enough, becomes soon a problem. So this is how I see the thing. If you, we will have no problem for well localized event not so far away, okay? Even intermediate localized event, if they are not so far away, with LSST, it will not be a problem. Okay. Then we are also limited by astrophysics, I mean, by the physics of the event, that if the mass ejected is small, if we are completely off axis or so on, this is a problem. For this off axis event, it's true that in astronomy, we are not well equipped. And this is due to the near infrared detectors, okay? That has a different stories than the visible detectors because of military reason, actually. So visible detection the visible filters are much more easily to have, to improve, to do some also R&D on them to make it more and more sensitive and so on. Near infrared detectors are still the benefit only of some countries. So it does make a limitation in this point of view. But it's true that gravitational waves are pushing us to also to improve a lot our way of working from the electromagnetic point of view, and the future instrumentation and the future use of the instruments that we are making.
Okay, So let's move to question. I see also an up. So let's start with the first question I have in my list from Chiara. So you, at some point, you can you go back to the slides in which you show this line curve in radio and compare with this bar, and you mentioned that it was right, this one. We just passed it.
Just a second. I went back instead of going forward. Just a second. It will arrive. Gosh.
It's not going
okay.
Linearly, right?
This one.
So the question is, which radio facility were you considering for the plot? Could you say a couple of words about how Theseus will help? I guess those are two disconnected questions.
Yeah. This is SCAP precursors. So ASCAP in Australia. It's a survey. I don't remember the name of the survey, sorry. That scans the sky regularly. These are the limits of this service. There were some first results published by Tara Murphy. I don't know if it was last year or a couple of years ago. They were focused on gamma ray burst, not on gravitational wave events, but you can see some details of the surveys in this result. And so this is, to my knowledge, the best we have to scan large part of the sky in the radio pretty quickly. Of course, when we will be sky. Sorry?
This is available today. I mean, this is a limit
currently. Available not. The data are not available. The survey is running. The survey is running. I don't know if they are really scanning all the sky that they can see or just part of them for the moment. I don't know the cadence, the strategy, let's say. But in principle, from the, let's say, what they announced, they scan the sky, that they can, large part of the sky every day. And 1 hour with the exposure, or 1 hour for each scans, let's say, of their field of view. So they have a field of view of 10 square degrees, okay? They serve it from 1 hour, then they go to the next zone and they scan a large part of the sky, and they repeat it every day.
And I
so
guess
to me, wait, yeah?
I guess that the square kilometer array is going to be a game changer here. Do you have an idea of how lower this black bar here would be?
Okay, then it depends on what they do. But if I'm not wrong, it can go down by more than a factor of 10.
Wow, okay.
Yeah, so this will be really a game changer. But since it's not an immediate one, so it will be for the 2030, but not for 04 and 05. That's why I didn't mention it. I mentioned LSST because in principle, already for half of 04, it can do something. So yeah, radio for sure will help a lot. So in the detection, for sure. The identification, if it is faint, it will be tricky without SKA. Okay, with SKA would be another thing. Then it will also depend how SKA will be used, because it's not said that SKA will have such kind of survey that scans the sky every. So the strategy, the synergy between gravitational wave detectors and SKAs has to be built. And it will be important to build it.
Can you comment on the Theseus as well? And maybe you...
Yes. So Theseus, the main, let's say, will have disadvantage here. It will have a very large field of view, but not only in the gamma rays, but in the X-rays. So it will be able to observe a large part of the sky and the X-rays, that mean with a good localization. So it will do, can I say, Swift, you saw Swift as a field of view of summer minutes, okay, per summer minutes, 20 minutes per 20 minutes. Instead, Theseus will have a much larger field of view in the X-rays with the precision of a Swift X-ray telescope. So it will scan the sky rapidly and will give you the detection of the counterpart with a very precise localization. So you can immediately follow up then from the ground. And there is also an infrared telescope on board. So in principle, this also can help, even if it is not very sensitive, but well, for the close by events would be useful. The other advantage is that of Theseus is, of course, in collaboration with future generation of gravitational wave detectors, because you will have a synergy also for the very redshift events on axis, for example, or almost on axis. You will have the gravitational wave counterpart detected by Theseus, because they will be too faint to be detected from ground. Let's say you will not have, without the gamma ray detection, or let's say the burst detection, you will not be able from ground to detect the kilonova or the relativistic afterglow if you are off axis, okay? Instead, with Theseus, you will have the detection of the short burst on axis related with the ET events, for example, the Aston telescope events. And there will be many of them, so this will be good. There is a paper that will be published very soon on the synergy of Theseus for multi-messenger astrophysics. Riccardo Ciolfi is the first author, and the Theseus collaboration is, the entire Theseus collaboration is involved, and has to be published, I guess, by the end of the month, something like that.
Okay. There is another question from Ayush. For gamma rays, will we find useful information in the future Cherenkov telescope array, CTA? Are they of use specifically for transients?
So our knowledge is based on what we know on gamma ray burst, okay? So for this topic, we know now that Cherenkov array telescope can detect emission at very high energy from gamma ray burst. This is not systematic, okay? So those are very rare events. It's still not clear if it is due to the performance of the telescopes that are available today, or if it is because only a precise class of gamma ray burst have such very high energy emission, okay? So we are studying to, within CTA, we are studying to, let's say, the best strategy to react to the gravitational wave alerts and try to detect the very high energy emission also from these events. I cannot say if it will detect them or not, and how many of them. We really know not so much nowadays to be able to give precise number. So in my opinion, there can be a synergy in the sense that I hope that we will detect some, but there is not a Cherenkov telescope array that will do the job, okay? Then of course, there are always a lot of information when we have very high energy photons on the emission mechanism of the relativistic jet and so on. So this is, for sure, there are very important observations, but those are not the ones that will detect most of the gamma ray counterparts of the gravitational wave events.
Very good. I see hand up from Il5. Il5, you want to speak up?
Yes. Do you hear me?
Yes.
Yes.
Thank you very much. I think it's best to speak instead of writing in the chat. So I'm just asking my question.
I agree. Feel free to do.
Yeah, thank you. First of all, thank you very much for this nice presentation. Have actually two questions about the detection. You mentioned that it's quite time limited because it's a burst happens and all the telescopes really need to really try to find out where there's burst from, right? And maybe I misunderstand or I'm not fully aware of how this activity is going on, but is it really all these sorts start happening once burst happens? For example, it's a merger happens, then telescopes start to search, or even the telescope starts searching, even the merger happens. So if it's a gravitational wave detector detecting an inspiral motion, and they already call it as the detection of the gravitational wave, then merger will happen within a day or seconds. Is it really happening, or is it the current searches always happen post, the mergers, then merger happens, then telescopes start to search? That is my first question.
Yeah, I answered to this one before your second one. So you have two questions in that. So the thing of being able to, so from the gravitation, let's say from gravitational wave interferometer, we don't have the information before. We will have it with future generation of telescopes for some mergers, like LISA will have this, will be able to alert us days before, for example. But this is not the current situation. So in general, we receive the alert and we react. This is not the case for gamma ray telescope, for example, because they are already observing the sky. So Fermi will be observing the sky. So he will see if he detected an event that is coincident in time, more or less, with the gravitational wave alert. Okay. The same for the gamma ray instruments on board the Swift. Okay. Then when there is an alert, Swift in particular, as a strategy to follow up the alert. So there are two steps. First of all, it can see if the gamma ray instruments on board, but has observed something, was already observing something time coincident with the alert. But then it can also slew to observe the sky map of the gravitational wave event. So suppose that he's observing here and the sky map is there, it will slew and start observing all the sky map region, in particular also with the X-ray instrument, that for which there are particular strategy of tiling all the region so as to be, let's say, to increase the probability to cover the region where is really localized the gravitational wave event.
Okay, thank you.
Instead, I have, sorry, just a precision. This is for gamma rays. I mentioned LSST. So LSST is scanning the sky, will be scanning the sky continuously, okay, independently of the gravitational wave alert. Then, so it may be that is covering part of the sky where the event took place, but then there is the possibility, but it's not been defined yet, that once there is an alert, the normal survey mode stops and the LSST the Vera Rubin telescope, therefore, goes and observes and scans the sky map of the gravitational wave event, okay? But this is still under discussion.
I see. Thank you.
I'd like to give a bit of information on the current situation there for the current ground-based detectors. So Susana correctly said that we are releasing the alert after the merger, because this is how our pipeline works so far. However, there are tested, there are current tests, and there is a recent paper about this, and possibly this is something that we'll discuss Neil Cornish next week, or maybe you can ask him as well, for releasing, for early warning alerts. So basically, alerts that are produced with the early part of the chirp signals, provided that there is sufficient SNR to release the alert. The drawback of this is that since you are using the low frequency part of the chirp, right? You don't have the merger yet. Your timing information is much less accurate, and therefore, since timing is essential to pinpoint in the sky, what we are doing is triangulation essentially. Then the error region in the sky is bigger, right? But you know that something is happening in a certain region in the sky. So maybe you can, alert those telescopes early on, and it may improve the success for discovery.
I see. Thank you. My second question is somewhat related with that. It's about the colors. The Susana showed that there is a dramatic difference between the blue and the red, for example. So if you're using only one band, yeah, we will detect the time variation of that band. But if we somehow simultaneous observations of the two band, for example, which have a dramatic difference in terms of the flux, will that be practically useful to identify those EM candidate quickly?
It's a good question, and this will be surely a good information to have. So one can identify also comparing the behavior at different frequencies, okay? Would be better to have many frequencies, not just one color, but also from the color we can have some indication for sure. This is, for example, it's an important point that to consider when you have to decide the cadence of your observation. For example, for LSST, I come back to that again, but it's pretty important. The cadence of the survey at the present state is not the best one to identify the counterparts, okay? This is also because there is also is foreseen to have, for example, just one filter and not to turn the filters. And so the strategy of the observations are really very important to identify or not, to be able to identify or not the nature of the transient you are detecting.
Very good. Well, so I think we are a bit behind schedule here. Maybe we can stop the recording. Can we? Don't go away. I have a number of important information for you. But let's stop the recording straight away. Ah oui. Est-ce qu'on peut arrêter l'enregistrement, s'il vous plaît? Est-ce qu'on peut arrêter l'enregistrement? Je ne sais pas, moi je ne peux pas le faire depuis...